so consider the inverse Fourier transform. Consider the inverse Fourier transform. I see that the inverse Fourier transform is 1 by 2 pi to the power n by 2 times the definition of inverse brings in this kernel e to the power I k x times the Fourier transform in the n dimension dk. Again this integral is not one integral, but a vector integral of for this vector k bar. Okay, so then I am going to change this inverse in over the hypersphere. So, this is going to be 1 by 2 pi to the power n by 2 integral 0 to infinity rho d rho integral now over all the angles over all the direction cosines e to the power I rho x dot u. So, that is my so that is what I have when I project it over the hypersphere f tilde of rho u du. Okay. So, what I have done here is I have projected over the hypersphere. So, this integral is projected over the hypersphere. Okay. Okay. So, then what I have is, notice that this particular integral, which is the interior integral, is the inverse of the Fourier transform, and then for the n dimensional Fourier transform on the hypersphere. So, I can replace this interior integral by its corresponding Radon transform. So, what I have is the following. What I have is that this integral is, now I am going to replace this definition of Fourier transform by the relation that I had in my expression 5 by its Radon transform equivalent. So, then what I have is this factor 1 by 2 pi to the power n by 2, and then that will pull in another factor 2 pi to the power n by 2 of the integral 0 to infinity rho d rho, and then so what I have is, well, this is over hypersphere S n minus 1. So, I must have rho to the power n minus 1. Okay. So, rho to the power n minus 1 d rho integral d u bar u, well, I am integrating over all direction cosines here, e to the power I rho x dot u. So, that is my kernel. Notice that now I am going to change my Fourier transform with the Radon transform. Okay. So, let me just multiply it with the Radon transform. So, I get that this integral is f hat of p comma u bar times e to the power negative I rho p dp. So, what I have done is using my expression 5. So, using expression 5, this integral has now been changed to give me a relation between the original function and its Radon transform. So, let me just write this lengthy long expression. Well, I must have one more integral to correspond to this inverse with respect to p. Okay. So, this is integral from negative infinity to infinity, and this integral is with respect to this element p. So, now we have come to this point using my expression written in my statement 5. Please see my slides earlier. So, I am going to now rewrite this entire lengthy expression into a very small compact notation. So, my notation is, this notation is 1, I am going to write it in a single integral as follows. So, this is also equal to the integral over all direction cosines of the function, which is a function over all hyperplanes times the arguments are the hyperplane values times and the direction cosines. So, I have the following. Okay. So, which means my function here, my function h of, let me just define this function h of t comma u. My function h of t comma u is 1 by 2 pi to the power n integral 0 to infinity d rho integral negative infinity to infinity rho to the power n minus 1 e to the power I rho times p minus t times f hat of p comma u. So, students can directly look at these expressions from this. Let me call this as my expression number 6. So, from 6 I have just used a very compact notation where my function h is defined by these 1 and 2, this rho integral and my p integral. Okay. So, this entire discussion, what I have shown here in this entire discussion is that I have shown you the formula for the inverse. So, I have shown you the formula of the inverse here. Okay. So, in particular, let me just write down what I have just shown. I have shown the following result. So, let me write down the result in the form of an inversion theorem. Okay, inversion theorem. So, what I have is that if I am given the Radon transform, let me denote it by f hat, Radon transform, and let Radon transform of f of x, then the relation that I have for its inverse is as follows. The inverse of the Radon transform given by f of x is related to its inverse as follows. This is also equal to the integral over the hyper surface of this function h of x dot u comma u du. Okay. So, where I have the following, where I have that h of t comma u is given by this expression. So, after evaluating the two integrals for this function h, I arrive at a very compact notation for this function. So, I have that this h of t comma u, the inverse, the relationship for the inverse function is as follows. This is also the iota, the complex square root negative 1 iota of n minus 1 of divided by 2 pi to the power n minus 1 of times the derivative, the n minus 1th derivative of f hat of t comma u for odd n. So, this is for odd n, and the other one is for the even n I to the power n 2 by 2 pi to the power n minus 1 times the Hilbert transform of the following quantity, the n minus 1th derivative of the function f hat of p comma u. Okay. So, this is for even n. Okay. So, this denotes the Hilbert transform, the Hilbert transform of the Radon transform of the function. Okay. So, what I have done is I have used a compact notation, a compact form of the function h of t comma u using the Hilbert transform, the Hilbert transform. Okay. And using integration by parts, Okay. And also I have used the fact that my Radon transform vanishes for the case where my hyper surfaces they reach to infinity or minus infinity. So, if the hyper surfaces are very far away from the origin, my Radon transform decays to 0. So, these two relationships are used to come to this compact notation of H. Let me denote this compact notation by my expression number 7, which gives me the inverse of the Redon transform. Okay. Well, it may not be very easy to see how we are evaluating the inverse of the function. So, let me give you some examples to show you how to evaluate the inverse. So, let me see what happens in the case of 2D. Okay. So, what I said is the following. So, in 2D, I am going to write down and find the inverse of the Redon transform. So, if I were to use my expression 7, I see that the Redon transform of the function. So, I get a function after applying the inverse, I get a function in 2 dimension. So, I get that the function is negative 1 by. So, this is, remember, for 2D the dimension is even. So, I am going to use the formula for my inverse for the even dimension, that is the Hilbert transform. So, using that Hilbert transform definition, I get that the expression is 2 times 2 pi and then the Hilbert transform 1 by pi, the Cauchy principal value integral of over this hyper surface du times the integral from negative infinity to infinity f hat of p comma u dp, okay, and divided by p minus x dot u. So, that is the standard definition of my Hilbert transform. Now, note that this particular quantity that I have used in Hilbert transform is the derivative of the function, well, the derivative of the Redon transform with respect to my variable p, that is the variable of the Redon transform here. So, f of p denotes the derivative of the function. Now, if I were to, let me call this expression as my 8. So, if I were to rewrite this 8 in polar coordinates, so in 2D polar coordinates, so using polar coordinates, let me denote x to be r cos theta, y to be r sin theta. I see that my u is cos phi sin phi. Well, so that is my direction cosine. I see that my f of r comma, well, let me say that this is, well, yeah. So, my function defined for the polar coordinate f of r comma theta, again rewriting my expression 8, let me call this as 8 prime. My function, the inverse function looks as follows. So, I get negative 1 by 4 pi square, here are all these factors here, times integral. Now, du, well, over all the hyper. So, this will be the surface of the sphere in 3D. So, this will be S2. So, over S2 my integration takes this form, integral 0 to 2 pi d phi, then the second integral is negative infinity to infinity f hat of p comma phi divided by p minus r cos theta minus phi, okay, dp. So, what I have used is the following. I know that my x, my vector x is the vector r cos theta sin theta, and the vector r is nothing but r, well, my vector u is going to be this direction cosine cos phi sin phi. So, after utilizing the respective dot product, I get back this factor in the denominator. Okay. So, then let me rewrite this expression here. So, let me denote this my. So, we see that in expression 8 and 8 prime, I have the relationship for the inverse of the Radon transform in 2D. Okay, so now I am going to look at another example. So, this was my example 1. So, let me see the inverse of the Radon transform in 3D. Okay. So, in 3D, let me call this example 2. So, 3D inversion theorem, 3D inversion theorem. So, now notice that if I were to use the inverse of the inversion formula, now for 3D case I have to use the expression for the odd dimension. Okay. So, that does not involve any Hilbert transform. So, the result says that if I am given that my Radon transform of f hat is well, f hat is the Radon transform of the function f of x comma y comma z. So, this is a function in 3D. Then what I have is, let me also denote this as r of f of x bar. Okay. So, x bar is the vector, it is a 3D vector. Okay. So, then what I have is that the function f of x bar is, well, so the inverse Radon transform is defined to be the negative Laplacian or the gradient square of the following integral, mod u equal to 1 f. So, this will be f hat, that is the Radon transform of the function for the arguments p and u. Okay. So, p and u du bar. Okay. So, we see that the inversion of the Radon transform in 3D is quite straightforward. So, let me give you the proof of this result, because this is quite a useful result. So, the proof follows. The proof is as follows. So, consider now the standard way to show the inversion of the Radon transform is via the Fourier transform. So, what we do is we consider the inverse Fourier transform. So, this is in in spherical coordinates I get the following result, f of x, this is also equal to, this is going to be the inverse Fourier transform in 3D over, so this is over S2. So, I am going to write the inverse over S2 here. So, this is, so my vector u bar is a unit vector on S2. Okay. So, S2 is the surface of the sphere in 3D. Okay. So, then writing the inversion formula, I get that this is also equal to, so I am going to use spherical coordinates. So, I am going to rewrite this inversion formula using spherical coordinates. So, using spherical coordinates I get the following result. This result is, so rewriting the integrals in spherical coordinates, I get the following integrals, integral s square ds times integral, well, over all direction cosines f tilde of s of u bar e to the power I s x bar dot u bar, okay, du bar. Okay. So, I see that the inverse of the Fourier transform in 3D has this form. This is over all vectors on the unit, well, all unit vectors on the sphere S2, which is the hyper sphere in 3D. Okay. So, then so since we are working in 3D, note that in 3D I have that the integral of du over this hypersphere is integral from 0 to 2 pi d phi integral from 0 to pi sin theta d theta. Okay. So, I see now if so that is my integration with respect to the direction cosines in 3D. So, let us now replace this integral in, let me call this expression as A and let me call this expression as B. So, let me use B in A to come to the integration over 3D, and I see that this integration is, so note that my original integral is over all values of s from 0 to infinity. So, and this is an even function. So, let me just double the integral from negative infinity to infinity and introduce a half. So, I see that this is also equal to half of integral du over all the over all s2 over s2 times integral negative infinity to infinity s square f tilde of s u bar e to the power I s p, and I see that this particular integral is evaluated over my hyperplane given by p equal to x dot u times ds. So, my integral element here is ds evaluated for all p which is lying on the hyperplane in 3D. Okay. So, then notice that the interior integral is nothing but the Fourier, this s square times the Fourier transform is nothing but the Fourier derivative, the second derivative of the Fourier transform. We all know that the nth derivative of the Fourier transform brings in a factor of s to the power n. So, which means that if we have an s square sitting in front of the Fourier transform, then this must be the transform of the derivative, the second derivative of the Fourier transform of f. So, let me just rewrite what I said. So, what I said is the following. So, now, so let me just before that let me introduce a minus here and a minus here. So, that makes, so my statement follows from this argument. So, what I have said is the following. What I have said is that my new integral now is negative 1/2 integration over S2, this is the integral over S2 over for all f hat the Radon transform of the Fourier, the second, the Radon transform of the second derivative of the f with respect to p. Okay. So, this is evaluated over the hyperplane. Okay. So, what I have done is I have used my result using the result of Fourier differentiation, Fourier transform, the differentiation of the Fourier transform, that is of the second derivative. Okay. So, we come to this expression. Now, note that this is also equal to, let me rewrite this integral again, this is also equal to the Fourier inverse, this particular expression is the Fourier inverse of s square f tilde of s u. Okay. So, what I have is the following. So, of course, this is evaluated over the hyperplane in 3 dimensions. So, notice that as I said that this s square is corresponding. So, the corresponding fact that we have an s square in the transformed plane, it means that we have a second derivative with respect to all the coordinates x, y, z in the physical plane. So, this means that this is also equal to the negative del square of this Radon transform. So, what I have is, this is also the negative Laplacian of the Radon transform of the function over the hyperplane with the direction cosine given by u bar. Okay. So, that is what we have. Okay. So, what I have shown here is the conclusion of my discussion is the following. I have shown here in 3D my inverse Radon transform is equivalent to finding the Laplacian of this integral, the integral over the hypersphere S2 of the Radon transform of, well, given by, so this is my P, so given by the arguments P comma U, okay, du here. Okay. So, I have shown you some specific cases of the derivative of Radon transform, namely the ones that I will be using for some of my practical applications. The derivative of, well, in 2 dimensions what happens to the inversion theorem, and in 3 dimensions what happens to these inversion theorems. Okay. So, then next I will be showing you some more properties, and then using this coupled with these inversion theorems we will solve some application examples. Okay. So, then let me introduce the adjoint Radon, transform. Okay. So, I am going to define another function called the adjoint of a Radon transform, and as the name suggests, the adjoint is going to be defined with respect to the inner product. Okay. So, adjoint Radon transform from the definition of the inner product, given by the following. So, let me introduce a function, inner product with respect to the function phi is of the Radon transform of the function f. The inner product is defined by the following integral from negative infinity to infinity dp times the integral over this hyper surface of phi of p comma u times the Radon transform, R, well. So, I define my inner product with this conjugate multiplication of this function phi with this conjugate of this function times du. Okay. So, I have the integration with respect to p and the integration with respect to u, and of course, this is not one integral, but the interior integral is a vector integral. Okay. So, then I am going to use my definition of Radon transform. So, let me call this expression star. So, I am going to expand my star, that is the conjugate. So, I am going to expand the star